A network cable is a length of metal. It has no awareness of files or websites or text messages. It only carries erratic pulses of electricity moving at a fraction of the speed of light. If a computer blasts a continuous stream of ones and zeros down that wire, the device on the other end faces a stream of random data. Without a coordination layer, these signals are interpreted as meaningless noise. Even when the pulses are clear, the system fails if the internal clocks on both ends aren't perfectly aligned. To make sense of the incoming voltage, the receiver must sample the signal at exact predetermined intervals. But hardware clocks drift. If the receiver's timing is off by a single microsecond, it begins sampling the signal at the wrong moment, reading a 0 instead of a 1 and instantly corrupting the message. Pushing electricity down a wire is a purely physical act. True data transmission requires a synchronized system of communication to impose order on that physical chaos. The simplest solution for this timing drift is asynchronous transmission. Rather than sending a continuous stream, this method breaks data into single character chunks. Each 8-bit character is packaged between start and stop bits. When the receiver detects that start bit, it resets its internal clock, ensuring it stays in phase for the next 8 ticks of data. This constant resetting comes at a high price. Because every character requires its own synchronization markers, the system loses 20% of its total bandwidth to overhead. That trade-off is manageable for short bursts of text, but as file sizes and connection speeds scale up, that 20% penalty makes asynchronous transmission inefficient for modern networking. To handle massive data loads, networks utilize synchronous transmission. This replaces small character chunks with continuous blocks of bits known as frames. Instead of bracketing every byte, specific flag patterns are injected at the beginning and end of the massive frame. The receiver uses that initial flag to lock its clock in phase for the entire duration of the transmission. This shift maximizes throughput, dropping the bandwidth overhead from 20% to less than 1%. However, as frames grow larger, they become more vulnerable. The physical environment is full of electromagnetic noise, and the longer a frame takes to travel across a wire, the higher the probability that a bit will flip during transit. A sudden voltage spike can cause a burst error, changing a 0 to a 1. Without a defense layer, the receiving computer would accept that corrupted data as accurate. Perfect timing efficiency means nothing if the underlying data is silently altered by the physical environment. Detecting this invisible corruption requires a rigorous verification protocol called the cyclic redundancy check, or CRC. Before sending a frame, the transmitting computer treats the entire sequence of ones and zeros as a single giant binary number. It divides that binary number by a specific polynomial formula, which outputs a short remainder. This remainder, known as the frame check sequence, is attached to the end of the frame and sent across the wire. Upon arrival, the receiver strips off the data and performs the exact same polynomial division through its own logic gates. If the data is intact, the receiver's division will result in a remainder of 0. If the result is anything else, the computer knows the data is corrupted, deletes the frame, and requests a resend. This process removes the guesswork from networking, turning the chaos of physical noise into a mathematical certainty. Requesting a resend works for local traffic, but fails in environments where a response takes hours, such as transmitting telemetry from satellites across deep space. These scenarios use forward error correction. This protocol allows the receiver to deduce what the missing information was and repair it instantly without asking for a resend. An encoder processes the original data and maps it into a larger, complex code word, packed with redundant logic. If interference corrupts the code word in transit, the receiver calculates the mathematically closest valid version, the Hamming distance, and snaps the data back into its correct form. By embedding the solution within the transmission itself, forward error correction allows autonomous networks to operate through high levels of physical interference. We have progressed from sending erratic voltage spikes to managing an orchestrated ecosystem of synchronized frames and self-healing code words. Every time a video buffers or a web page loads, this invisible scaffolding is executing these protocols millions of times per second. While generating data is a simple task, ensuring that information survives the journey across oceans and space requires constant, silent cooperation between machines. The internet functions because of the logic running in the background, ensuring every bit arrives exactly as intended.